getting a little bit more complicated in physics, we can analyze for a water hammer event. And so what I have shown up here is really just a very basic analysis. And so we have temperature and pressure specified here. We have a mass flow rate, and actually one thing we need to do is load some startup conditions to it. So one thing I haven't talked about is snaps. And so snap is a snapshot of not only the boundary conditions, but the model state at every single element in your model. And so if we had solved, let's say, according to whatever operating specs I have, after 10 minutes of operation, then 3 different events can occur. And so what I can do is solve for 10 minutes of operation, store that model state in a snap, and then use that as my starting point for 3 different transient scenarios. So there's no need to rerun that 10 minutes every single time. So all this is right here is specifying or loading my previous models, and so I had been playing around with this offline. And so what we're doing here is specifying a mass source of minus 200 kilograms per second. One thing that I haven't talked about is when we place elements on the page, there are arrows that indicate flow direction, and that's not limited. The model isn't limited to only allowing flow in that direction, but if you depending on the results you're looking at, so if you start to see a negative mass flow rate, then it's just relative to the arrow direction. And so since this is an outlet condition and we are applying minus 200 kilograms per second, that's essentially pulling that mass from the system. What I have over here is an accumulator. And so what we'll see is I have a transient event defined that says, sorry, I should have cleaned up my work before the actual presentation. So what I'm doing is at time equal 0.1, an event occurs. And so the event can have multiple actions that are going to occur, such as a valve closing, a pump tripping, some type of heat input being applied. And then each action has another trigger. And so this is essentially saying at time equal to 0.2 seconds, what happens is that this boundary conditions mass flow rate is going to go through a line function modification. And so it's going to assume this type of equation of 2,000 times time and our constant, since we're starting out with minus 200 kilograms per second. And it's going to go through this modification until it gets up to an upper limit of 0 kilograms per second. It's an upper limit because we are applying a negative mass flow rate. And so what this is going to do is for 0.2 seconds, it's going to pull fluid through this system, and then it's going to start shutting that off, and what we'll see is pressure waves through here. One thing to note is that in order to get the previous transient analysis to solve relatively quickly, or solve quickly in a meaningful way, we used a rather large time step. And so for this, the pressure waves that develop are pretty fast. And so what we can do is I've created a button that just changes the time step size. And I did that just by inserting a button and having this link to the solver time step. And then I can how to animate, and by animate I mean turn green or red depending on whether it's in an on or off status. So what I'm going to do is, just so we can track what's happening in our analysis, I'm going to drag and drop, go to my select icon, drag and drop this guy, and what I want to track is just the pressure at that node versus time. And so I'm not going to run this for very long, and so I'm going to increase my sampling rate so that way the total number of points matches my time step size, so I don't get any type of weird line divisions. And that should just about do it. And so what I'm going to do is I'm going to solve my steady state just to initialize. I'm actually going to turn this off so it doesn't waste time trying to plot that. And now if I were to click run, we start to see these huge pressure spikes as that as the pressure wave travels back and forth and eventually dampens out. And so a thing to note here is that the material, the working fluid in this model is just a single phase liquid representation. And so in reality, what's happening with these negative pressure spikes is we're actually going to be changing phases. Because we're dipping below the vapor pressure. And so, we can capture this type of event, but if we actually wanted to track, how much liquid goes to vapor or anything like that, we could then apply a two-phase material model to this and actually track quality versus time. And so what we see here is we get these huge pressure spikes. And so we're going to play around and just insert this accumulator. And so this accumulator is essentially a cylinder with a gas charge in it that's going to act to dampen it out. So by doing this, I'm first going to load my snaps. And as soon as I load this, my mass goes to minus 200 kilograms per second. Make sure I reset my time. What I'm going to do is I'm going to copy, and I'm going to paste. And so right now, when you copy and paste, there's no persistent link between the elements. So if I make it a change right here, that change doesn't propagate back. And so this is a way where you can start with a very basic model and slowly work your way up in complexity. And so all I'm going to do right here is I already have the properties for this accumulator defined. So all I'm going to do is just connect this to that pipe. And what I want to do is make sure that I've turned the solving off just because those were kind of some free-floating elements that didn't have any working fluid assigned to them. And so if this solving is off, this is a nice way for you to troubleshoot your model. So you can basically turn the solution for different elements on or off, and so you can troubleshoot what the actual problem is. Just want to make sure that that's solving. And what I want to do here is I also want to plot the pressure on this guy. You see that by default, when you plot two different items, it's going to create two different y-axes. And before I can solve this, I just need to modify my transient event. And so all I need to do here is apply the same event to this mass source. And so at point 1, I'm going to have, you can have all these different type of value modifications. And so if you wanted to have some type of sinusoidal mass flow rate, you can define that. For this, I'm just going to be consistent. 2,000 minus 200. Specify that I have an upper limit of 0, and I am good to go. And so all I'm going to do is solve my steady state. And now when I click Run, we see this blue. The blue represents that initial one, so that's the network that is not protected. And then we have this other line, the green line, if you can see. And the important thing is it looks like it's actually spiking, but let's look at the y-axis here. And we see that we're not going from 5,000 to minus 5,000. So what I can do is come over here and specify that I do not want multiple y-axes. And so when I plot these both on the same scale, you see that my accumulator is effectively preventing these huge negative pressure spikes, which would be damaging to the system. And so I think I'm doing okay on time. I got a couple